Hello, everybody, and thank you for joining the second day of the workshop on earthquake damage mitigation for collections, which is led by Jerry Podany and Mackenzie Lowry. My name is Sagita Miriam Sunara, and I'm an associate professor at the Conservation Restoration Department of the Arts Academy in Split. And I would like to introduce right away my colleague Dunja Vranešević from the Museum Documentation Center in Zagreb, as Dunja and I will be moderating the program. And we are joined also by Iva Valigia from the Museum Documentation Center, who is providing technical support. Dunja, over to you.
The Earthquake Damage Mitigation for Collections workshop is organized by the Museum Documentation Center and the Conservation Restoration Department of the Arts Academy in Split. We are very pleased with the interest that the workshop has raised. We have received almost 200 applications from Croatia and other countries in the region. So this truly is an international event. We are very fortunate to have been able to organize a workshop which is led by such distinguished experts. Just to remind you, Mr. Podany is a leading expert in earthquake mitigation for collections. He is the editor of the book Advances in the Protection of Museum Collections from Earthquake Damage and the author of the book When Galleries Shake, Earthquake Damage Mitigation from Museum Collections. So I'm showing you once more, I'm like a hostess here. So Mr. Lowry, whose presentation we will hear tomorrow, is an experienced mount maker in the area of seismic mitigation. They both worked at the J. Paul Getty Museum in LA, which is, as we heard and saw yesterday, located in a seismically active area. So working at that museum, they spent years, even decades, exploring this topic. Sagita, please continue.
Thank you. So from the presentation that Jerry Podany delivered yesterday, we learned that we cannot control, nor can we accurately predict earthquakes. But that we also learned that there are experts who can help us understand what level of earthquake we can expect in our area. And Jerry stressed that we need to have an understanding of some basic terms in order to be able to actively participate in conversation with such experts. And once we know what we can expect, we can start preparing for it. And today, Jerry will talk about developing a sense of vulnerability of a collection to the expected level of earthquake. Now, before Jerry takes the floor, I would like to remind everyone in the audience to please keep your microphones and cameras off during his presentation. If you have any questions, please use the chat section at the bottom of the Zoom window, or you can wait for the discussion session, which will be held at the end of the day, and then you can ask your questions live. Now, Croatian members of the audience, if you wish to type your questions in the chat section, you can do so in Croatian, and then Dunja and I will read your questions, translate them to English.
I would also like to remind you that the workshop is being recorded and that by participating in this event, you consent to video recording and its release on the YouTube channel of the Museum Documentation Center. I will give you a link in the chat for our channel. Jerry, the floor is yours.
Thank you, Dunja. Hello to all again. I hope the time over the evening while you slept, you dreamt about response spectra. Yesterday, we explored in a rather general way the nature of earthquakes and how we record and measure them, and how, again, in a limited way, we use statistical methods to forecast the inevitable seismic events in certain areas and within defined periods of time. And you will remember there we go. And you will remember that I emphasized throughout the talk the need for the use of a multidisciplinary team to tackle the challenge. Before I begin, I want to backtrack a bit about, regarding a question that I believe Vilejo asked about what should you do right away. And my response was that you should search the literature, inform yourself, and then began to develop this team of experts to help. However, I should have added that while you're doing that, you should do what is practically necessary, what is simple. And in many cases, we'll illustrate those today. But for example, if you walk by something that wobbles while you walk past it, it's probably not going to stand up during an earthquake. Or as I mentioned, if there are very heavy things on the very top shelves in your storage room, put them at lower shelves and anchor those shelves to the walls. Those are things you don't necessarily need experts to do, but they can go a very long way in preventing a great deal of damage. To begin with, I want to recognize and thank all of the following institutions you see on the screen, institutions and collections, for their generosity and foresight. Each was involved in sharing documentation about the damage that occurred in the recent earthquakes in Croatia. As we mentioned yesterday, this is exactly the kind of input that is necessary for all of us to move forward toward a better risk management and toward improved resilience in the future. I am indebted to all of them for their generosity and certainly applaud their transparency. Through those efforts described yesterday, we're able to define the hazard we face and then prepare for it and hopefully mitigate its effects. And you will remember the amount of vulnerability that is reduced is a matter of deciding how much potential damage is acceptable. You remember that equation of tolerable risk must equal acceptable damage. But how do we know what degree of vulnerability we have to the hazard of earthquakes? How do we define it? And how do we understand the degree of risk we're taking? Today, we're going to explore how objects respond to earthquake ground shaking, the forces that are transmitted through the building into the object. Within that broader question, we will review how we can predict that response, knowing as we do now the worst case scenario that has been planned and the basic volumetric weight distribution of the object. How can we change that response to assure more stability during the earthquake? We'll briefly look at the protection of collections in storage. It's a good reminder to say that earthquakes don't stop just in the galleries. They continue everywhere throughout the building, including in those areas of storage. And we'll look at collateral hazards. We mentioned them a bit earlier in terms of floods, burst pipes, landslides, explosions. I even mentioned civil unrest and security issues and our potential lack of ability to control the environment. But there are many other collateral hazards within the building and display area, as well as storage, that we need to pay attention to. Now that the museum has established the nature of the earthquake threat that it faces, and it has determined the level of risk reduction it's going to commit to, again, the level of risk that is tolerable, it is time to both determine vulnerability of the collection to that level of ground shaking and initiate mitigation measures to protect the collection. Determining vulnerability requires that we understand how an object might respond to the earthquake energy that's being transmitted into it through the building, through the floors, through the walls, through fixtures such as exhibition cases and platforms and pedestals. In all instances, the building and the fixtures may attenuate or reduce the energy, or they may amplify, that is, increase it. So referring to the building's response spectra, as you remember, you can develop a response spectra for a building itself, referring to that spectra as a source of knowing the peak acceleration, the peak velocity, and the peak displacements, as well as the dominant frequency of the design earthquake, are all important. And as you know from yesterday, it is possible to estimate that through probabilistic seismic hazard analysis. How the objects respond ultimately defines the risk level, which may be different for different parts of the building or different aspects of the collection, or in different ways that the object is stored and displayed. A bit later, we'll look more fully at the many ways of collecting data and of organizing it for when you do your vulnerability survey. For example, you might organize by degree of vulnerability. You might organize by value of the objects, or the object type, or its fragility, to name just a few. But first, we need to better understand how objects might respond. Now, there are 4 basic ways that objects might respond. The object may move with the building. Normally, this means that the object is either attached to the building or is so heavy and that it won't move, or easily tip over. Either way, the object remains unaffected by the fact that it doesn't move independent of the building, it moves with the building. But it also receives all of those transmitted forces through the building that we spoke of earlier. The objects will might rock, or they might vibrate, or they might swing if suspended. They perhaps may be damaged in such an instance by the accompanying pounding when they rock back and forth, or the object may, what is termed walk, vibrate over a distance. And that includes that it might walk off the edge of a shelf, or it might walk off a pedestal and fall to the floor. Or perhaps, as it's moving, it might collide with another object, or the wall, or the inside wall of an exhibition case. Thirdly, the object might slide and perhaps be damaged by sliding off the edge of a shelf or pedestal and fall to the floor. Or perhaps it may slide into another object and collide. Or while sliding, it may engage with an irregularity in the floor and then suddenly overturn. Or if suspended, it might swing and collide with another object or the wall. And finally, the objects might overturn and be damaged by impact, or may fall from the suspension hardware due to the fatigue of that connection. In the last 3 models, the object's response might lead to damage of other nearby objects due to collision. In so many cases throughout the world, collision and overturning is probably the lead cause for severe damage to objects and collections. And by the way, I should mention the arrow at the bottom of each of these models is the direction in this particular illustration. That's the direction the Earth is moving. And it's always good to keep in mind that when we talk about objects and their stability, we often think about walking over and giving them a little push and seeing if they're stable. It's a good technique, but in earthquakes, it's the floor that's moving. So it's like pulling the rug out from underneath someone. And it's good as a reminder to say that the forces and displacements are not caused by something pushing the object the way we normally think about it, but because the ground is moving from underneath it. It's a matter of changing your perspective. And I don't want to give short shrift to objects which are suspended, may swing, collide into the walls, or other objects that are suspended nearby, or more commonly, the connection, for example, this long chain or cord, this connection right here may fatigue because of the extensive swinging and may fail, allowing the object, in this case, a chandelier, to fall. And you remember yesterday, we talked about vertical movement as well. And to change one's perspective in severe vertical movement, the ground may heave upward and then suddenly drop. And for a very short period of time, just a microsecond, the object actually is free floating. And then suddenly it will catch up and there'll be a sudden impact, a sudden jerk downward. And so these connections become very important for suspended objects. And that's true of paintings as well, which might be suspended from the wall, from wires connected to the wall or to a rack in storage. But during the earthquake motion, may move forward and then come back, swing back and hit the wall, or they may swing side to side and collide with each other. Now, which of these response modes the object might enter is predominantly determined by two inherent characteristics of the objects themselves. The location of the center of mass, also sometimes known as the center of gravity, and the aspect ratio, also sometimes termed the slenderness ratio. In addition to these, is at least one outside characteristic, and that's the coefficient of friction between the object and the supporting plane. And by supporting plane, I mean the pedestal top or the shelf surface or the floor surface, etc. Let's first look at the aspect ratio. Or, I'm sorry, let's first look at the center of mass. The center of mass is a theoretical point where all the forces acting upon the object are focused. For the average human form, for example, the center of mass is just below the navel. The lower the center of mass is, the more stable the object is. The term stable here refers to the object's inherent resistance to rocking and overturning. You see here, in these cases, because they're very simple geometric shapes, the center of mass is also the geometric center. So here's the center of mass for this lens, center of mass for this column, center of mass for the cube is found right in the middle by connecting all the various centers, geometric centers of the sides of this shape. The aspect ratio, the second of the most important inherent qualities in an object, is simply the relationship between the height and the width arrived at by dividing the smallest footprint dimension by the height, base divided by height, or B over H. The larger the aspect ratio is, the more stable an object is. So, a tall, thin volume will be less stable than a short, wide volume. These two shapes that you see on the screen have very different aspect ratios. We can use this rather simple geometric shape, a rectangle, to illustrate the concept of aspect ratio. Oops, oh. There we go, sorry about that. If it seems as if, and indeed it is, intuitive and common sense that if you turn the rectangle on its side, the aspect ratio is more favorable towards stability and that the center of gravity is closer to the ground, as you see on the bottom example where we've turned the rectangle on its side. Now, if I asked you which of these three shapes or these three assemblies would be most stable in an earthquake, I think you would intuitively say the tall one with the spherical mass on top would be the most unstable shape. And indeed, you'd be right. It's simple, really, if you come to think of it. And yet, over and over again across the world in museums, we find this kind of display. And often these collections are in highly active seismic areas where earthquakes are neither rare, nor should they be any kind of surprise. And equally often in such displays, these kind of exhibition approaches end in damage and loss. This illustrates what we're trying to overcome through a better understanding of the threat, of the object's response, and of mitigation plans that would reduce damage and loss. I want to stop for a moment. I thanked all of the collections and institutions for sharing their photographs, and I was very sincere in saying I applaud their transparency. And I think it's important to point out that showing examples like this is in no way a criticism of their approach, of their previous approach to exhibition. We can only learn how to improve our mitigation efforts by learning from these sorts of examples so that we can improve our approach. So by no means is this criticism. Now, every once in a while today, I'm going to take a moment to try to remind you of the strength of earthquakes. This is one of the largest test facilities in the world. It's in the mountains north of Kobe, Japan. These are two full-size, two-story dwellings. They are actual size. These little things up here are engineers observing the test from a distance in a control room. They are both mounted to shake tables, and the input into that shake table will be the time history. You remember time histories, the recording of the amplitude of an earthquake by a seismograph, and that information will be input into these two shake tables. One of these buildings has had retrofitted mitigation, so it's the structure has been built in a way that will protect it against earthquakes. So should these structures experience the Kobe earthquake, this is what will happen. So to say the least, you want to live in this house. Perhaps more germane to our discussion, however, is what happens on the inside of the house that survived. They outfitted it with furniture and office equipment the way you might experience in a house. This is the same thing, but from the inside. This poor guy here, right? An earthquake doesn't distinguish between a dwelling, an office space, or a museum. And I want to remind you that because something we don't often think about, that within an earthquake, when it strikes, objects that are unstable could in fact be life-threatening to the visitors who, in this instance, might be trapped in a stairway where a large sculpture has collapsed. Now let's take a look at the inherent degree of stability or instability of objects and how we determine that. There are numerous methods of determining the characteristics of the center of mass and the aspect ratio, as we just spoke about. Increasingly, they involve scans, digital scans of the object to create digital models that are analyzed by computer programs such as finite element analysis or versions of finite element analysis, such as programs like Scan and Solve. However, both the center of mass and the aspect ratio can be generally arrived at through the creation of simplified two-dimensional geometric models analyzed through often tedious but not necessarily complex calculations. I'm going to go through just a few of those today as a demonstration, but I'm increasingly inclined to recommend the use of digital programs since they are far less susceptible to human error, which is common given the length of what might be called traditional hand calculations. Still, however, at least understanding such calculations can shed a good deal of light on the basic concepts we're pursuing. And for those institutions or individuals who at this moment in time can't afford the services of digital modeling and finite element analysis, they are a potential way of arriving at similar conclusions. We've already seen these two versions of a simple rectangle where the center of gravity matches the geometric center, achieved by simply drawing two diagonal lines, each connecting the opposite corners to arrive at a common intersection where the center of mass is located. Again, this is a two-dimensional model, not a three-dimensional one. The aspect ratio changes by turning the shape 90 degrees, as we saw previously. The rectangle that's lying down has an aspect ratio of 3 versus an aspect ratio of 0.3 for the rectangle oriented vertically. Intuitively, of course, you would have already known that the rectangle laying horizontally was more stable and less likely to tip over. Unfortunately, though, most objects or object assemblies, by object assembly, by the way, I mean objects mounted on pedestals or objects assembled with platforms. These object assemblies are not simple shapes like this rectangle, but they can be modeled nonetheless if they're composed of simple shapes, such as a series that I showed you before. Let's look at a very simple geometric shape to begin with, which might represent an object attached to a pedestal. Both have their individual centers of mass and individual aspect ratios, both of these forms. Let's call this the object, and let's call this the pedestal. But since they are joined together firmly, we want to consider them as one object, an assembly that will respond to the seismic forces as one unit. Note as well that in this example, the two volumes are of different weights. However, you will note that the center of mass of both objects align along a single vertical axis. The object is centered on the pedestal without any eccentric elements. So this is a very simple model. To start, we determine the center of mass for each of the two segments. Since they're relatively simple, we can use the geometric center of mass simply by drawing intersecting lines. Here's the center of mass, and here's the center of mass. They align along one single vertical axis. But notice that this one is 56 kilograms, and this one is 22 kilograms. To start, we determine the center of mass for each of the two segments. Since they're relatively simple, as I said, we can use the geometric center. We then apply this formula. Now, the result of this formula that we're seeking, lowercase h prime, is the height to the center of mass of an equivalent block, which we'll define in a moment. As you can see, the center of mass as calculated by that formula is 36.2 centimeters above the floor. But because the two shapes don't have exactly the same footprint or cross-section, though the coordinates of the center of mass align along a vertical axis. We need a second step, so we apply this formula. But in order to apply that formula, we need to know what this is, so we calculate that here. Ultimately, using the data we have, this formula results in us knowing that r squared equals 1,693 centimeters squared. So now we can plug that into the previous formula, and we find that our equivalent block, this, has a height of 57 centimeters. Notice the H here is capitalized. So this is the total height is 57 centimeters. And that would mean that the height of the center of gravity of that equivalent block is 28.5 centimeters above the floor. Notice that it's slightly lower than our previous, more simplified calculation because we've taken into account the difference in footprint. I should probably tell you, and I should have probably said this earlier, the equivalent block is simply the geometric shape that is calculated when we look at both of these centers of gravity. So this is a representation of this. The width of the equivalent block is the smallest width that the lowest and smallest width of the assembly right here. And then the height is calculated through the various formulas which I provided. So now we have a generalized and simplified geometric equivalent of our object and pedestal assembly. Remember, we're assuming that the two volumes are rigidly attached to one another and they will move as one thing. So this is not simply placed on top of this pedestal, it is anchored to it. And that will become increasingly important in the rest of today's discussion, as well as tomorrow with when Mackenzie talks about mounting and stabilizing objects. We can now utilize a tool called a stability chart. Oh, sorry, that's the equivalent block. The stability chart, which is developed based on characteristics of the design earthquake, utilizing data reflecting the peak velocity, the peak acceleration, and to some small degree, the peak displacement of the design earthquake, the earthquake which we expect statistically to happen based on the amount of risk we have determined is tolerable. Such stability charts can be developed by engineers or seismic engineers and are quite useful in placing objects in general categories of stability once the design earthquake scenario is determined. The chart you see here on the screen was developed for the Getty Villa Museum and the worst case scenario earthquake for a return period of 476 years, what we thought at that time was reasonable, and a peak acceleration of 0.7 g. So about 3/4 of a g would be our peak acceleration in our design earthquake. It is customized for that design earthquake scenario, and it is meant only to illustrate the concept. It does not have universal applicability since each design earthquake and the response of each site and each building will be different. So I'm using the Getty Villa stability chart as an illustration here. If you were interested in developing one for yourself, it would look slightly different. Now, back to our object and pedestal assembly, you can see that the equivalent block with a total height of 57 centimeters and a base width of 38 centimeters, or an aspect ratio of 0.66, lies very close to the dividing line between stable and rocking. The stability chart divides, generally speaking, based on base to height ratio, the objects into a zone of stable, likely to rock, and probable overturning. So this object is quite close to rocking. Now let's look at a much more complex object, this copy of a Roman bust. Note how small the footprint is. Intuitively, you're already thinking that it is unlikely to be very stable. Well, let's see. First, we divide the object into a series of simple geometric shapes, as we talked about previously. Then we follow the same calculations we applied to the previous example, though this time the task is more tedious and much more involved. And I should add, by doing hand calculations like this, much more susceptible to human error. From that, we know the height of the equivalent block, this block. And we know the width of the equivalent block, which is the width of the part of the object that contacts the floor, or the width of the base. And as you can see, the stability of this object under the conditions of the Getty villa design earthquake is very poor and is well within the overturning zone. But you already knew that, right? Now, stability or instability of any given mass, if the earthquake force is known, can be calculated, either through the general guidelines, such as the stability chart, or through separate equations, such as these, which include sliding. For example, this block right here could have been evaluated in terms of the likelihood that it would overturn in the 2011 New Zealand earthquake, and might have led to actions that would have prevented this. And over it goes. I'm going to play that again in order for you to also consider the life-threatening aspects of earthquakes. These are parts of a ceiling tile and display board that has crashed down from the ceiling. This is one very lucky individual. But at this point, I must note that these calculations are really quite general. They are simple shapes with a force applied in one direction only, and only at the center of mass. The forces are static loads, that is to say, they're not dynamic, not changing, and from one single direction, and with a single acceleration and velocity. Earthquakes in reality are simply not like that. They're dynamic in every sense of the word. To demonstrate that point, here's a video of a shake table test. This is a replica of a large ancient pot. That's me trying to salvage the pot or prevent it from falling over because they're not cheap to make. The action of the shake table is the Getty Villa design earthquake. You remember that's the one with a 476-year return period and a peak acceleration of about 0.7 G. And you'll remember a G force is equal to 1 gravity. So we just fed that design synthetic time history in, and this is what we expect the ground to do. And if we were to just place a pot on top of a pedestal, if we were to place a pot on top of a pedestal, this is what would happen. I'm not actually touching the object, I'm just trying to save money. You'll note that the forces come in all directions, except up and down. We're not capable of producing that. And the object almost turns over, and then there's a little bit of an extra push. And that's what overturns the object. That's what's called dynamic motion, and it's considerably different than those simplified geometric models that I was showing you. I look forward to a time, of course, when we can model the object in the digital realm and then expose it to the design earthquake in all of its complexity. We certainly can scan objects now. We can certainly create digital models. The ability to put those models in a dynamic digital world with design earthquake time history is a little out of reach for most cultural institutions. But it wasn't that many years ago when the idea of cleaning sculpture with laser light was extraordinarily expensive and extraordinarily exotic. It's still beyond the reach of many institutions, but it's becoming more common. So my hope is in the future, we'll be able to scan an object, put it into a digital environment, expose it to dynamic motion, and understand how it may respond. But for now, the calculations that I have offered and that are in various publications that we've mentioned at least gets you closer and are certainly better than nothing. So, having reviewed all of this information, how can we increase stability and reduce vulnerability for all objects and object assemblies? Well, you probably are already intuitively thinking that there are several ways in which we might change instability. And we can adjust the aspect ratio, or we can adjust the center of mass, or we can restrict or restrain motion, or we can allow some motion, but within a restricted range. I'll touch only briefly on the latter two, since they'll be covered thoroughly and in some detail by my colleague Mackenzie Lowry in the next session tomorrow. In this session, we'll explore changing the location of the center of mass or the aspect ratio to be more favorable to stability. Now, there are several ways in which we might change the stability of that first rectangle that we discussed. We can adjust the aspect ratio or the center of mass, and we can restrict all motion, or we can allow restricted motion. The center of mass can be lowered by changing the weight distribution, usually achieved by adding weight to the object or the object assembly, or attaching it to a lower mass of greater density, that is heavier, or by adding weight to the object itself, or by changing the aspect ratio. Let's look at both approaches. Here's a simplified example of a column. In the first instance, weight is added. See if I can point to it without changing the slide. There we go. Here's the first example. Weight is added to the column near the bottom, and you'll see that the equivalent block is now just a bit shorter because we've added weight. Alternatively, to the right, a base with a larger footprint has been added. And in the final version on the far right, the same base has been added, but it's now much heavier. We will call these versions A, B, C, and D. A is the original column, and B, C, and D are the improved versions. Let's look at how that plays out with their equivalent blocks graphed on a stability chart. You see that A is clearly in the probable overturning, and that B, where we've added all of that weight, remains in the probable overturning. However, by changing the aspect ratio, that is, giving it a wider base relative to its height, in C, we've moved it all the way over here to the stable area. And by adding weight to that larger base, we've moved it even further into stability. Although given the amount of effort and material required to add weight here, we haven't moved it a great deal. And notice that given all of the material and effort to add weight to this pedestal, we've moved it only a little bit over and not removed it from probable overturning. So I think you can see how a stability chart, if developed for your design earthquake, your probable worst case scenario, is helpful in generally categorizing the stability of objects and how you might increase that stability. Now, part of this suggests that by adding weight, we can adding weight can sometimes be advantageous, although it's not as effective as increasing the footprint dimension. But in fact, sometimes adding weight has completely the opposite effect. Let's look at this column. Here we have a column and a column with added weight, a column with very little added weight, and a column with a lot of added weight, almost up to half of its height. A here is probable overturning. B is just barely into the stable area. C, well, it's going to rock, maybe it'll be stable. But D has, for all intents and purposes, not left the probable overturning area. Despite all of that weight, it's still pretty unstable. And that's because at some point, it's almost self-defeating. You raise the weight so high that the center of gravity of the equivalent block starts to move upward from here to here to here. So adding weight is not always the answer, but changing the aspect ratio certainly will help. I'm trying to be cognizant of time, so I think this might be, let's see, this might be, well, let's look at this one. Here's a kind of a real life example where we have a pedestal, a hollow pedestal with an object, again, firmly attached. We've calculated the center of mass for all of these. We've added a large footprint platform. All of these are well connected. And we get a very low center of gravity a very stable equivalent block. So, looking at this slide again, I think you now are fully informed about why this kind of exhibition approach of very narrow, thin pedestals with large, heavy objects on the top. These objects are attached to the pedestal, which is a good start, but the pedestals are not attached to the floor. I think you can see why logically and intuitively and through calculations, these would surely fall, overturn and fall into the area of instability. There's my slide for a break. So Donya or Sigita, how about if we take a 10-minute comfort break and return back?
Yes, of course.
Yeah,
yes.
That sounds great. So in 10 minutes, we will be back, and thank you all. See you in 10 minutes.
Button.
Okay, can you hear me? Am I on? Good.
Yes.
In just a few minutes, I'm gonna pause and ask you if you have any questions. We're about halfway through, and if you have any questions or comments about the material that has been discussed so far, I'm happy to address them, or at least try to address them. So what we found in the previous section is that there are ways of measuring the inherent stability or instability of the volumes that objects represent. We can calculate their equivalent block and use that information to apply some very simple calculations, static calculations, as to their stability. In those static applications, we're applying forces that are informed by our previous study about what the likely earthquake might be. In the case of the Getty Villa, the likely earthquake produced a peak acceleration of about 3/4 of a g-force. So in our calculations for those simplified geometric models, we applied that force to the center of mass to see if it would not move, if it would start to rock, if it would tilt slightly, if it would overturn, or including calculations about the coefficient of friction between the object base and the floor, that is, how easy it would slide, or how difficult it would be for it to slide. We could calculate whether if we applied that force to the center of mass, it would slide. And I mentioned that those simple static calculations are not quite realistic. In fact, they're not realistic at all in terms of earthquakes because of the dynamic motion in earthquake. They're better than nothing, and they help you to put objects into general categories on that stability chart in the fields of stable, rocking, or overturning. But they don't really reflect the kind of dynamic forces that occur in earthquakes, where motion is coming in any direction and is constantly changing. The amount of displacement is changing, the amount of forces are changing, the amplitude is changing. And so they aren't fully realistic. I'll demonstrate, well, here, let me take this picture of my granddaughter, right? And you'd think of it as a rectangle. Now, in our static condition, we would apply a force at center of mass, and we would know whether it would do this and then return, do this and return, probably do this and start to rock. Or it's possible that we would apply the force and it would do nothing. Or we would apply the force and it would slide. Or we would apply the force and it would overturn. But as you saw on the video of the shake table, what happens is that it starts to rock perhaps, and then at some point we'll freeze it at that point where it's rocking. We'll freeze it right there. And now an additional pulse from the earthquake occurs, and it doesn't take a lot to continue and overturn it. So this dynamic motion changes the complexity of the analysis considerably, which is why we'd certainly look forward at some point in the future to a user-friendly interface to a program that would allow us to apply dynamic motion that was also affordable for most of us in the heritage sector. So I would be happy to clarify anything that we've covered so far, if you have any questions. Who will moderate?
Okay, Jerry, so Dunya and I are keeping our eye on the chat section, but we don't see, okay, Anna Stolar, okay, there is somebody who has a question, and it's a colleague from the Museum of Arts and Crafts, Anna Stolar. She had some questions yesterday as well. And Anna, maybe it doesn't make sense that you type questions. If you are comfortable with it, you can switch your sound. I see you have your camera on, so please feel free to ask Jerry.
Hi, Jerry, and hello to everybody.
Hi, Anna.
Hi, nice to see you again, by the way. I just wanted to ask a couple questions regarding the last part of the lecture. One is, do you assess all objects? If you have, hundreds of thousands of objects or millions of objects, that's a lot of time and effort put into it, because these are serious calculations that take a lot of steps. And the second question is, if we can go back to those busts and pedestals, and if you could tell us what would have happened if they were attached to the floor itself.
Okay, so for the second part of your question, we'll look at that in detail in the second half of the lecture, but how these forces might affect the material, the material characteristics, the strength of the object will determine how they're affected. If they're anchored all together and restrained from motion, of course, all the forces that come through the building from the ground are going to be transferred into the object. For the first part, no, I mean, there is not nearly enough time in a single lifetime to go through all of those calculations for each object. It would, again, be nice if there was some way we could digitally, or there is a way of digitally modeling them, but then input that into a digital environment where they're tested. For now, we don't at least have that ability. I'm sure it's out there somewhere, but it's exotic and expensive and requires a great deal of training to run it. So into the future at some point. What we do instead is try to and we'll talk about this in the vulnerability surveys, we try to characterize the objects and place them in generalized groups, right? So we have not one bust, we have perhaps 20 busts or 50 busts or 100 busts. And they're all about the same distribution of mass and distribution of weight. So we can generally assess their center of mass and generally assess their response through perhaps running the calculations on one or two representative examples. And then eventually, as you start doing more and more of that, the intuitive part comes into play, and you start getting a sense of how stable an object will be. I'm going to put sense in those air quotes, right? Because you can become overconfident of that. So on occasion, you want to stop, run some calculations, and see if you're still on track. That is for the most simple of objects. When objects become very complex, when they have eccentric masses or they're made of many different materials, running those calculations can be very useful. Did that help?
Yes, very much
Good.
so. Thank you.
Good.
Okay, so if anybody else has a question, feel free to type it in. Okay, we have something from our colleague from NEMO, which we mentioned to Jerry earlier on. The question is as follows. In your experience, does it make sense for museums to combine their evaluation and preventative efforts regarding earthquake preparation with other natural disaster emergency plans? Do you feel that varied preparations are too conflicting to be addressed simultaneously?
So I think I understand the question in terms of trying to develop response plans to a range of disasters. Although this workshop isn't necessarily about responses, they are intimately linked, the effort to mitigate and the effort to respond, because you also want to mitigate while you're responding. I mean, your respond plan should include measures that you undertake so that you don't increase the damage. Whether or not, how much you can combine the various response plans for different hazards together and not end up with a massive multi-volume response plan is a matter of looking at each one of the hazards, looking at your vulnerability for all of those hazards, considering how you will respond to all of those hazards, and then looking for commonalities in those responses. And those commonalities will form your major response plan. And onto that major response plan, you will have addendums that are specific to each hazard. You're not going to necessarily need a lot of sandbags for a tornado, but you might if it turns out that the flood is a collateral hazard due to bursting pipes, for example. In a discussion about earthquakes and a response plan to earthquakes, it is by the nature of earthquakes always good to have lots of addendums, because as I pointed out yesterday, there isn't just one black swan, there are many black swans. Earthquakes can cause internal and external flooding, tsunamis to broken pipes. They can cause explosions. The list is very long. So I would suggest that you develop a response plan for each one of the specific hazards, and then you filter through it and you look at the commonalities. You develop the major plan, and then onto that you have addendums that can customize actions of your major plan to fit that hazard. And we can talk a little bit later if you want about emergency response issues. I started researching and doing workshops on emergency response all the way back in 1983. And it was for decades rather frustrating. We would go to a collection and ask how many of them had a response plan. 2 or 3 hands would go up. 2 years later, we'd circle back around to that same group and ask the same question, and 2 or 3 hands would go up. It's a hard sell. However, it is much better today than it has ever been before. The literature is full, to bursting, of ways of developing response plans. Not so much for mitigation, not so much for what you would think would be our preference, which is to do work ahead of time so we have less to respond to. That's our next major consideration. Then the last thing to say about your comment, which came to mind, was I think museums should bind together, and it's nothing is more frustrating than finding out that everybody continues to invent the same wheel over and over and over again. museums should come together to share resources and to share information, and there will always be some individual needs that don't match other needs, but generally speaking, they should work together because it's going to become more expensive and more common and more complex to respond to disasters as they start to pile on top of one another. And so we need each other, and we should start using each other now to develop more effective plans.
Thank you, Jerry, for that response. I hope that Elizabeth is content. I don't see any new questions in the chat section. Yes, she says, thank you for your response. An excellent approach. The increase in discussion of emergency response plans is very interesting, and we cannot agree more that museums need to work together on this, and who better to also inspire and support these initiatives than Nemo. I wanted to ask you, Jerry, and then you can maybe continue with the remainder of your presentation regarding the stability chart that was developed for worst case scenario for the Getty Museum, which you showed. Who created that chart? Who plotted it? Was it some external contractor, or was it you and your colleagues?
No. I don't have the training to create such a thing. It was an external contractor, an engineer who was working with us, and he utilized the information from the response spectra that we developed with that return period. And predominantly, it's based on the peak velocities and the peak accelerations of our design earthquake. That is the one that we accepted at the time as being almost our worst earthquake, and the one that we're going to design everything toward. So most seismic engineers should be able to develop such a thing. There is a reference to the article which that particular engineer wrote about designing these stability charts. That's in my book, and I think in a couple of other articles. And the engineer you're working with can certainly reference that if they don't know how to do this already. Again, and thank you for asking the question, because again, it allows me to emphasize that these are general tools. They're extremely helpful, especially if your collection is large. They're really helpful, and they're a good jumping off point, but they are generalized tools. And that's often said in everything that has to do with earthquakes, because there is so many unknowns, but at least it gives us some basis to work from.
Excellent. Thank you so much. We shall keep the other questions for the end of today. So maybe Jerry, you can have a glass of water if you need a bit of refreshment, and then
Okay.
and then you can take on. And please, everyone in the audience, feel free, use the chat box to ask your questions. You can write them in Croatian and Dunja and I can translate it, or you can wait for the end of today's session and then ask Jerry in person. Thank you to Anna, who joined the live discussion. So I shall turn my camera off, and Jerry, you can continue. Thank you.
Good, and thank you for those questions. They were excellent. So far, we've focused on the center of mass for a single plane in those two-dimensional calculations, usually the front view. But of course, the center of mass is a point in 3 dimensions. This can be envisioned by calculating with the same procedure from the 2 sides, the back, as well as the top and bottom, and then averaging or finding the intersection of all those points to arrive at the coordinates of the center of mass in the entire 3-dimensional form. Oops. Certainly, one of the other options is to restrain the motion, and this is where we're going to get to the previous question. For example, a sculpture can be installed in such a way that it's anchored to the ground or the floor, or anchored to something that in turn is anchored to the structure of the building. However, It's important to understand that while the object will certainly not walk, overturn, the forces that result from the building responding to the ground motion will be directly transferred to the object. And the object must be sufficiently robust to withstand those forces if it's going to survive without damage. Transmitted forces can result in a wide range of damages. The object can crack if it's a brittle material, or it can tear, or it can deform if it's a more malleable material. And it may, if somewhat flexible, continually respond by waving. In this case, in this configuration, it might wave back and forth until it fatigues enough in a vulnerable place that it tears. Knowing the forces that will occur in the design earthquake, developed with the methods described yesterday, in yesterday's session, a finite element model can be created of the specific object type and those forces applied to the center of mass. Finite element analysis is a very common technique. It's not terribly exotic, and it's available for reasonable cost to anyone through consulting firms. The resulting maps, much like the one you see here, or the one you see here, will indicate if the stresses created in the sculpture will be greater than the strength of the material the object is made from. Now, there lies the rub for most cultural heritage objects. You have gone through all the trouble of determining the worst case scenario for your level of toleration of risk. And you will now scan the object. You will submit it for finite element analysis, and they will impose the forces, the peak accelerations and velocities that occur according to the design earthquake scenario. However, the engineer will then say, well, what's your object made of? And you will say something like ceramic or stone or wood or ivory or glass or whatever it is. Or you will say to the technician, well, it's made of several materials, at which time the analysis becomes far more complex because each of those materials respond differently to the forces, and their intersection will make things even more complex. But if we back up, let's say that we think it's a simple marble sculpture. What are the material strength characteristics of that marble? Well, first you have to know the type of marble. Do you trust your eye sufficiently to say if it's Carrara, a very fine-grained marble, or one of the island marbles with very large grains? Those two marbles have very different strength characteristics. Or perhaps it's a dolomite, or a limestone, or a granite. Perhaps the bronze is brass, or bronze with a high tin content, one more brittle, one more malleable. Perhaps the ceramic is high fire, porcelain, or perhaps it's low fire. On top of those complexities, we have to add how, if the object has weathered, is it weakened by weathering? Are there fractures that we can see? Are there fractures that we can't see? Are there inherent voids or fractures that we can't see that aren't caused by time, but are caused by the formation of the object itself? Are there casting flaws or cracks in the ceramic due to drying and firing? And finally, Are there repairs and restorations? Is the object all ceramic or is part of it plaster? Is the connection between the restoration and the object itself secure, or is it just put together with some aged shellac that's now brittle and weak? Or are there pins joining the various parts of the object? So you can see that it is not by any means a simple process, but there are assumptions that you can make. I can't necessarily list and tell you what those assumptions are. Those come from your familiarity with your collection and with your efforts in the past or in the future of producing accurate and thorough condition reports for each of the objects. We'll talk more about that aspect when we talk about vulnerability surveys. But part of those surveys have to include an understanding of what the object is and its inherent as well as accumulated fragility. And all of that information feeds into the kind of analysis that I suppose we could call high tech. And not to go on too long about this, but I might add that even engineering materials where they can take very large samples, do a whole series of tests to determine the physical characteristics and strength characteristics of the material, they don't necessarily always agree either. If you look for example, the strength or even the Poisson's ratio of Carrara marble, you won't get one number. You'll get a whole range of possible numbers, partially because tests are different in different places. Forces are applied at different rates. They're not as consistent as they should be, but also because one place in the quarry compared to another place in the quarry will produce a material that is slightly different in strength. So engineers normally come together and will try to use the average, or they'll add extra safety factors by using the weakest number rather than the strongest number. All that has to be worked out with the engineer that you're working with or the technician you're working with. But it is possible to at least know where the major stresses are going to be, as in the case of this finite element analysis done through Scan and Solve program. You see the stresses build here. This is assuming that this object is rigidly attached to the ground. And I think we applied about a half a G-force to this. And so this area, if I can get my mouse to work, there we go, this area is where all the stresses are building up. Sometimes that's pretty intuitive. You would know that. Other times, the stresses in this model climbing up the side of the figure were unexpected, but good to know. Now, Mac will cover this in much more detail than I will or I'm capable of, but in a museum environment, restraining motion might include also adding strength to the whole system. So here it's a simple brace, contour mount. These are models. They're not the sort of thing, the finish you would see in a gallery exhibition. They're intended only as demonstrations. So you see here, this prevents the object from moving or overturning. The same here. And here, it not only prevents this fragile object from moving, but it also adds stiffness to the entire system. So the object is not connected to the surface. It's only held in place and supported by a mount. And that, again, will be covered with in tomorrow by Mackenzie. Now, it's time again to consider the forces. Normally, when we see videos of an earthquake, we see objects moving all over the place with their surround, pedestals rocking back and forth. At one point, we decided that we would look at the object while the camera is moving with the object, right? So this is a typical, and maybe this addresses part of that question as well. This is a model of a bust. I'm going to turn off all the sound here so that you're not distracted by it. This is a model of a bust where, in this case, there is a pin that is a small pin that is anchored into the pedestal top here, and it goes into a hole in the bottom. It's not, the pin isn't glued or adhered into the object at all, and it's very short and woefully small, pretty common in a lot of museums. Right? In this case, we have a contour mount coming down this way, and a couple of small stops, just pins that come out of the pedestal and touch the side of the object to prevent it from sliding at all, although this mount also prevents it from sliding, but this is just additional restraint to prevent sliding or rotating. And then in this final one, we have clips, which are also very common in museums. So a metal clip that is attached to the top of the pedestal and fits over the edge of the socle base here. There's one here, there's three of them, and that attaches the object. But there's something extra about this one as well, in that the pedestal itself slides on the surface of the shake table. Here, the pedestal is affixed to the surface. So I'm showing you these without going into too much detail to give you an idea of the kind of violence that occurs when an object experiences the Getty Villa design earthquake on top of a tall pedestal. It takes a minute for there we go. So you see the object is rocking like crazy. Eventually it tips over enough to disengage from the pin. The pin doesn't go back in the hole and it pushes it off the side. Here, oh, sorry. I'll let you hear the sound. So in this case, the object didn't fall over, but you'll see because of this gap that what happened is that it rocked enough that it rode up on one of those little pins that was preventing it from rotating. And it did quite a bit of damage to the edge of the socle. And here, this is the one with the clips, and it's the one where the pedestal is allowed to slide. So the point of that is that the object was restrained. It still received some forces being transmitted up through to the object through the pedestal, but the forces were minimized, and there wasn't any pounding, and there certainly wasn't any overturning. Now, having talked about sliding, the other major way in which we can prevent damage is to allow the object to slide, or to essentially decouple from the ground and let the ground move under the object without influencing in any major way the object itself. If the object will slide if the coefficient of friction, as I said, between the object and the supporting plane, that is the floor or shelf, for example, is sufficiently low. In most cases, the rougher one or both of those surfaces are, the greater the resistance is to horizontal movement parallel to the plane support. The advantage of allowing an object to slide are that the pounding associated with the rocking is avoided, and forces that would be transmitted to the object are, for the most part, eliminated because the object has become, as I said, decoupled from the support plane. However, there are a number of quite serious precautions that need to be taken. First, the plane on which the object slides must be consistent and without flaws. A discontinuity in the coefficient of friction might abruptly increase the resistance to sliding and allow the object to overturn. That is to say, it's sliding along just fine, and it hits a discontinuity in the floor, a bump in the floor, a piece of bubble gum, whatever it might be, and suddenly the coefficient of friction changes and the object overturns. If the sliding is somehow not limited, or the area in which the object can slide within is not large enough to accommodate the expected displacements, the object may collide with other objects or the wall, etc. And remember, in the response spectra, you can get a sense of the peak ground displacement that might occur in an earthquake, and that can give you a sense of how far an object might slide. The disadvantage of letting things slide by not restraining them is that they can slide right off the shelf or right off the pedestal and collide with the floor, or as in this case, collide with objects on a shelf below them. Here are a number of slides where almost certainly the object slid or toppled off a shelf above it and became, in its falling, became a collateral hazard to the objects below it. I'm going to show you an interesting thing about sliding, one of the benefits. This is a very small shake table, a model of a ceramic vase. It is not attached to the shake table. And there's a piece of typing paper, just plain white typing paper, scotch taped to the top of the shake table in order to increase the coefficient of friction, that is, to make it harder for this object to slide. The input is the peak point of, I believe it was the Northridge earthquake. So it's not the full earthquake, but it's the peak. Here's what happens when you have a little bit of friction. Off it goes, falls over, right? Overturns. Now, the only difference here is that we've removed the piece of typing paper, just regular typing paper. And now the coefficient of friction is such that this object easily slides on this surface. Oh, sorry. You see what has happened? We have decoupled the object from the ground. And as long as the ground motion isn't too severe, as long as it is reasonably thoroughly decoupled, and as long as there's enough room that it's not going to jettison off the shake table, the object is actually quite well protected. Now, here's another example which doesn't work out quite as well. Here's a what used to be the traditional method of exhibition at the Getty Villa. Very tall, very slender. Pedestal made of solid marble. Pin, this is a model of a head of about the equivalent weight of the original, made of concrete. What we're testing is we know that this configuration would not be stable in the design earthquake. So we're trying to add plates. We're trying to change the aspect ratio. And this is on a very smooth, consistent, slick surface, a slab of granite, polished granite. And underneath the added width plate here, the plate that adds width, that changes the aspect ratio, we've put little buttons of Teflon. So this should slide and protect the object, was the theory. This is the design earthquake for the Getty Villa, and it includes vertical. And you'll see what happens is that the object starts to rock, but then because the coefficient of friction is so low, it doesn't complete its rocking, it sort of slides, but it's still pounding. It's better than overturning, but it's still something that allows the forces of pounding as it lifts and slams back down as it walks to transfer to the object. So it's a degree of protection, but certainly not as complete as we would like. So let's talk for a minute about, again, about collateral hazards. We covered the issues of external collateral hazards pretty thoroughly. Again, landslides, fires, flooding, explosions, etc. But there are also seemingly innocent elements within the display and storage environment that can quickly turn into hazards themselves. We already had several examples of where, as they fall or as they tip over or as they slide or walk, objects themselves can become collateral hazards to other objects, crushing them or fracturing them as they collide. Also very common are non-structural parts of the building failing. False ceiling sections, ceiling tiles that come loose, or the entire lightweight aluminum structure that holds the ceiling tiles may fail and collapse onto your objects in the exhibition area. Temporary or false walls, these sort of display walls that are put up to divide spaces during an exhibition. They have to be sufficiently robust to withstand earthquake forces, otherwise they will fall and impact the objects. Signage and label holders. One of the damages that we had at the villa during an earthquake was caused by these plexiglass, they're thick plexiglass sheets that are bent at a right angle so that the label is put on the vertical side and then they're just set onto the shelf. We didn't think about that. We didn't think that that could become a hazard. And one of those labels started to slide, one of those label supports started to slide on the glass shelf, got all the way to the edge, and there was just enough space for it to fall off the edge of that suspended glass shelf and then hit a pot below it and chip the lip of the pot. From that point on, all labels were fixed down with wax, or labels were changed to be on buildups or external to the case itself. Lighting fixtures are notorious, these long extensions with heavy cans and light bulbs at the end of them and a very small, often twist connection to a track lighting. They will start to swing just like that chandelier we saw. And eventually that connection will fatigue, or rather quickly, that connection will fatigue and that entire weight will come down. May come down in an open space and you lose a few hundred euro to replace the light. It may come down on a visitor, at which time you have much more serious problems, or it may come down on an object or a group of objects. Lighting grates, or whether they're in the ceiling, or more commonly, lighting grates that are inside of exhibition cases. You know, it's those sort of honeycomb grates at the top that diffuse the light inside of a case. They are rarely designed to withstand the kind of distortion of the case or the kind of pounding and rocking and movement that the case experiences during an earthquake, and they will often fall and crush the objects below them. Shelves are just an enormous problem throughout the world. At some point, I don't know what that point was, but at some point, we designers and curators and directors and everybody in the museum became very enamored with the idea of a glass exhibition case and then these suspended glass shelves. The aesthetic was, if you prefer that, the aesthetic was very pleasant. The problem is those suspended shelves are very heavy and they are now like a little pendulum inside of the case. So as the earth starts to shake, they're going to start to swing, they're going to slam into the inside surfaces of the case itself, and eventually they're either going to break or they're going to fail in their connections, or they're going to slide away from their connections and they're going to fall with the objects on them onto objects below them. It is an extraordinarily common source of damage in museums in earthquake zones. Then you have the multitude of many other things that you normally don't think about in the museum environment. Air conditioning ducting, pipes, whether they be water pipes or sewage pipes in the ceilings that not only can fall, come dislodged, but they can also, the joints can break, and then you have water, whatever the pipes contain, coming into the galleries, and you then have a whole nother level of collateral hazard. Now, these are just a few of the problems. As you look around your institution with new eyes, I think you'll see that there are many others. These too have to be taken into consideration and dealt with. Often the solution is very simple, very low cost. You buy a few 1 or 2 euro brackets to secure your lighting grate. So they're reasonably easily resolved. Let's look at some real life examples on your right. The objects in the case in the Archaeological Museum in Kobe, Japan, would probably have been fine. They probably would have survived the earthquake. But these lighting grates that were at one point up above inside the case here were not well connected, and in all the cases they fell, and in many cases they did extraordinary amounts of damage. Here you see glass shelves that were not sufficiently anchored inside the case, and they have broken or they've fallen, broken, and then crushed the objects. Here, such a typical example of suspended glass shelves. This one simply fractured in half, the object down and doing damage. Just as an aside, this is a very small example of it. Often you have very big objects in a case and they've fallen over to the inside of the case. Trying to retrieve that object is is a real problem. Trying to open the case or lift the case without damaging the object can be really difficult. Here's an instance, I'm sorry, it's not collateral, but here's an instance where the object is not connected to its pedestal. I think the pedestal was probably connected to the floor, but the object was just sat, I believe, on top of the pedestal. And of course, it overturned or walked to the edge and then overturned. Here's a really good example of an object becoming a collateral hazard. So my assumption is that this object, where's my cursor? There it is. This object fell and fell upon this plate. This object probably wasn't damaged, but this object is severely damaged. And this object, well, that object, just lucky, it was far enough out of the way. Here's an example of, I'm not sure it's either an exhibition case or something that was intended to stand vertically, which has fallen over, and you see lots of glass. Don't know what was in it or on it, but it's an example of, it could be an example of a dividing wall, temporary wall, that's not sufficiently anchored. Now, I would be very remiss if I didn't mention objects in storage, because they are not immune to the forces of earthquakes. All the principles described so far apply and apply directly, though restraint of the objects is somewhat easier since there are fewer display aesthetics to be concerned with, although accessibility, of course, is always an issue. You don't want to protect the object in a way that would restrict accessibility in storage or make it so complex that every time a scholar or curator wants to look at it, they have to go through a bunch of steps to get access to it, because the likelihood of them always going through those steps is pretty low. So you don't have to be so worried about aesthetics, but you should make the object easily accessible. Here's an example that is really common throughout the world. Although the shelves in this case are pretty substantial, they're not anchored to the wall, and there is nothing to prevent those shelves from falling over, and there's nothing to prevent those shelves from rocking and slamming into the wall, thus creating a really a dynamic situation where the objects themselves will almost surely start to rock, collide with one another, and overturn, rock, or slide off the open shelving onto the floor, as has occurred here. And here, where the shelving is anchored to the floor, but the weight of the objects are such that the shelving has started to collapse. Very fortunately, it didn't, but it could have. Here, a storage shelving unit has collapsed and fallen over. I like to believe it was in the fortunate direction and not in the other direction where it could have damaged the vessels, but there may be damaged objects behind it. This is all to say that a very simple effort of moving shelving to a wall area and anchoring that shelving to the wall, or anchoring shelving units together to make them a more stable overall mass, or lowering the height, adjusting the aspect ratio of the shelves, and always putting the heavier objects on the bottom, the lighter objects on the top, and always making sure that the weight distribution on the shelves is appropriate for the structure and strength of the shelving unit. There are so many things that can be done in storage areas that are so inexpensive. If you don't want objects to slide off the shelving, you can use commercial plastic netting or tie lines across the surface, or you can increase the height of lips along the shelf edge here, for example. You can pad, loosely pad, in between objects with preservation-safe foam to prevent collision. You can nest objects in, again, stable material like ethafoam, cutting a form-fit nest so that they're accessible, but they're protected. And you can do that within shelving units, or you can do that within boxes. Boxes are always a good idea, right? As are open slat crates. You can attach objects to structural elements of the building, or you can strap objects to shelving that itself, the shelving unit itself, is attached to the building. Or you can allow the object to stand within an open slat crate that's more stable. All of these are really extraordinarily common sense solutions. It's just the issue of being aware of the problem. Now, I wanted to leave a considerable amount of time for discussion so that I can clarify anything that might have been confusing to you. I addressed earlier about what you might want to do first, and that again is to familiarize yourself with the research and the literature that's out there. Start developing a team around you that will address this issue. But while you're doing that, do some of those obvious things. It is so easy to look in hindsight during the survey of the damage. Oh, if we only would have anchored the shelving, or, oh, I always knew that was going to fall over, and sure enough, it did, right? It's always easy to look back on that, place blame on people, feel guilty about it, whatever it is. But you need now to move forward, and you are informed about what you can do, how you can evaluate the situation. Matt will talk to you tomorrow about the very specific steps of mount making. But the more you study this, the more you observe, the more it will become intuitive and second nature. And as you start to do those simple things, you will not only feel more secure about the safety of the collection, but you'll be able to build on that experience to more specific and perhaps much more complicated efforts. The point is, I guess, once you're familiar, and I hope now you are more familiar and somewhat informed, and I hope now you are somewhat more informed, repeating those same mistakes and not learning from the past, as Director Kotyan mentioned at the beginning of yesterday, the beginning of this workshop, equals willful ignorance, which I know you will overcome, and I know your collections will now be in safer hands. I list my email there. I'm happy to respond to email inquiries. It might take me a little bit of time, but happy to do it and be helpful where I can. So I'd like to stop there and open up the floor for questions and discussion and comments.
Jerry, thank you so much. Before you stop sharing your screen, I just wanted to ask you if you can go to the previous slide where we have the covers of the two books, one book which you edited and the second which you authored. And if you can just say a few words about the content of each of them. So the first one, the advances in the protection of museum collections from earthquake damage, that was connected to a conference organized by the Getty, right, back in 2006, if I'm not mistaken.
Yeah, this was one of the first of a number of conferences, mini conferences that we put together. I was very interested in taking essentially the same format of information and take it to different countries and include experts from those countries within that format to spread the word about the fact that you can do a lot to prevent damage in earthquake mitigation. We went to Turkey and to Japan and to China and to Sicily, but this was one in Los Angeles at Villa. And it was an effort. Well, there were many purposes, but one of the ones that I was most interested in was bringing together seismologists, engineers, sometimes architects, conservation professionals, museum designers, and mount makers and other technicians and collections managers to bring them all together to see how those pieces, like the plates, like the tectonic plates, fit together as a puzzle to achieve the one purpose, which is to increase resilience and to protect collections to lower risk. Those all went really well. How much impact they had is hard to gauge because working on seismic mitigation is a very steep hill to climb because you're working against, as the director said in the beginning, against a natural inclination to kind of put bad news out of the way. And you have to always be worried about, or at least cognizant about the hazards that are there. But with the idea that we can do something about minimizing those hazards, it's not a depressing topic at all. It's actually pretty positive. So that was the source of that one. And then when Galleries Shake were just, writing a book about it and getting it out there was on my bucket list. So I did that. I don't get any kind of income from these books. They belong to the Getty, so I'm not pushing them for that reason. I would love, I desperately would love to be putting up slide after slide of other books, of other research. I would love that. It's increasing. There are more people involved, but especially the combination of the younger generation of engineers and the younger generation of conservators coming together to work together would be just ideal for me. And to see more books, more articles would be great.
Well, we are grateful for you for having provided us, the conservation and heritage community and museum community, with such fantastic publications. So thank you so much for that. Now, I think that we are ready to start the discussion. But before I start reading, we do have some comments in the chat section. But what actually I would like to do is to kick off from the end of your presentation, where you tackled the topic of seismic mitigation measures in storage, or how earthquakes affect objects in storage. And I would actually like to ask Iva Valigia, who is in charge of the technical support of our workshop, to share with us some images that were taken at the Ethnographic Museum in Zagreb, where the so-called reorg workshop was held, which is a workshop aimed at improving or reorganizing storage areas based on the methodology that was developed by ICROM and the Canadian Conservation Institute. So Eva, if you can, or if you are ready to share the images, excellent. Eva, you need to turn on your microphone. I think if you want to make some comments on the images that we are seeing.
Yes, I just needed to find where is the microphone when I share the photo. So you can see the two photos before and after the reorg. Before, the items were, some of them were on the shelves and others were laying on the ground. And what we did is, with the relatively no money or little finance, we succeeded in ensuring the items in the case of earthquake by wrapping them in bubble paper, bubble plastic, and putting the security bands around the shelves. It wasn't a big cost, but it's very efficient to a certain degree of earthquake.
Excellent, thank you, Eva. Do you want me now to share a few images?
Yes,
that you
please.
sent me? Okay, just give me a second.
Listening to all this lecture, I realized that we have a situation in Croatia where we did all the wrong things. Even the museum that opened its permanent display last year has those glass shelves that are, in this case, these are not museum items, they're only models. But it's such a big hazard. Potential damage of an earthquake could be really big here. So it seems to me that we are doing the same. We are not educated maybe or informed enough to try to prevent all the possible damages from earthquakes or other different situations. I try to remember, here you can see my son looking at it, and I try to remember, I'm fortunate or not fortunate to have twins who like to walk very fast through the museums, and now I remember, as you mentioned, how many museums I've been to and been aware of the sound of the glass when they're walking a bit faster through the rooms. It's not only Zagreb, or it's all along the coast, in every old building where the exhibitions are, I'm afraid.
It's an excellent point you made, and then maybe Jerry, you can comment on this. And I think that Maya Kocian, director of Museum Documentation Center, she did leave a question in the chat section in which she actually is asking, are glass shelves in these display areas, are they something that should be avoided or not, Jerry?
Well, first, I want to say congratulations on that retrofit of the storeroom. It's a perfect example of low cost, common sense, informed decisions. And
they had a minimal damage during
no doubt. And that's always, that's a great feeling. I mean, if your big earthquake happens and everybody's trying to get to the site, and very often you can't. Nor should you necessarily enter a building, because that may have been a big earthquake or that may have been a foreshock, and you don't want to put yourself in danger. And in many countries, you're prevented from going in. So for days, weeks, sometimes longer, you're wondering what happened. The more you can do the sorts of things that you just demonstrated, the less you have to worry, right? The less damage will occur. Now, glass shelves. I understand the aesthetics and the beauty of glass shelves. I'm not questioning that. I'm just questioning the ways in which they're constructed. So glass shelves should not be allowed to swing around freely. That's just asking for trouble in seismic areas. The connections should have many safety factors. They should be robust. They shouldn't be I know it's lovely to see these thin rods and sort of minimal little clips that hold the glass shelf, but it's not going to withstand the kind of forces we're talking about. Glass should never be simple pane glass. It should always be tempered or robust safety glass, because you don't want something to shatter. You know, it's bad enough if it breaks. We have seen retrofits. We did one at the villa where earlier, where constructed metal support rods that went under the glass and then connected out to the glass edges with sort of bumpers, so it would minimize movement and also add structural strength to the glass. But I think, so there are a number of retrofits you can do to try to salvage the situation. If you're at a point where you're making a decision, just don't use glass shelves. You know, don't make that decision to begin with. We see, however, in so many contemporary institutions, this kind of modern to contemporary look of the clean designed line with minimum intrusion, and that often equates to weak structure and problems in the future. So it's a problem we have and we have to deal with. I would very much like to see, you know, some young PhD student, let's say, doing a survey of the kinds of the basic kinds of glass shelves, the basic kinds of supports, the basic kinds of approaches to design, and run them through a shake table and see what happens, and then show the results, and then work on a number of retrofits and show where retrofits don't help and show where retrofits do. I mean, I've seen glass shelves in museums that are big, thick plate glass extended from the back outward, not touching the sides or not touching the front. Big shelf extended out from the back by inserting the glass into a little slot in the back. With nothing anchored it, just inserting it into this slot and letting it cantilever out onto the surface and then loading it up, right? Because the logic goes, it's a thick piece of glass, so we can put lots of objects on it. But it's the connection in the back of this cantilever that's going to fail, either because of the bouncing that occurs during the earthquake, or because it's simply going to slide out of that slot, or it'll bounce out of that slot, and then it comes down. And there's at least two examples I know. One was really very sad, of a glass shelf that was suspended on these thin metal rods. And it wasn't an earthquake, it was the subway train that passed by the earthquake on a regular basis. And over the years, no one noticed that the glass shelf slowly and eventually just slid off, vibrated off. One of the sets of supports came down and completely crushed the objects that were glass below. So it's not just earthquakes that these glass shelves, and in general, it is not just earthquakes that the structure of exhibition furniture has a problem with. But reviewing them for earthquake safety is a good way of reviewing them for all the other problems they might have. The Tullio at the Met, the pedestal wasn't sufficient for that kind of weight, and it was constantly moved around. And one night, in the middle of the night, it fell, right? And the sculpture broke into an enormous number of pieces. So we have concentrated mostly on objects and their stability, but all of those same principles apply to exhibition furniture.
In Croatia, in Zagreb, many museums building are close to the trams and close to the traffic, and so yes, that also makes some kind of movement in exhibition area. Yes, I would like to go back to the theme of storage rooms and ask maybe Veljko Đikić from National Museum in Belgrade to join us. He was mentor in reorg project, and maybe he would like to share with us some of their efforts and maybe measurements that were included in their projects.
Well, hello everyone. Thank you for giving me the chance to speak in this very interesting course. Well, over the years during these reorg workshops I've been involved in, we often ask participants to have their view on the risks present in the storage areas. And most of the answers were always concerned about relative humidity, temperature, pollution, whatever, dust. So very rarely we receive the worries about the risk of the earthquake damage. However, in workshops that were prone to earthquakes, like in Croatia, we actually only took concern about this risk. Because it was something that you already mentioned, it was very easy to do and very, very common sense. So we did something similar in Greece and in Northern Macedonia as well. Now, Eva already showed the approach that we applied in the ceramic storage, but I would like to share with you another idea, let's say. Unfortunately, I don't have a photo, but I will try to explain it to you. So in a contemporary museum in Skopje, in capital of North Macedonia, we had a lot of freestanding sculptures, and eventually they were put on a double row of plastic pallets, so heavy duty pallets. And finally, we couldn't anchor them to the pallets, and we couldn't anchor them to the wall because they were in the middle of a room. But nonetheless, we again used the rope to tie them all together, sort of make a loop around them. And actually, the earthquake struck North Macedonia, I think 1 year after the workshop. And from the response that we had from the curator, some of the sculptures, leaned on the rope, but they didn't topple over because they were bounded by the other objects, so creating a more sort of a heavy mass that prevented those border objects from toppling over. I guess it's similar to the idea of when making a transport. So we always try to, for example, tie several boxes together with a stretch foil or some other means in order to create a larger volume, a larger single volume that will not easily move or turn over. So that's just another idea that we try to implement whenever we have a chance. But I wanted also to ask you, Jerry, about the difference in approach between the storage items and the exhibition items. Obviously, for various reasons and justified reasons, the objects on display are basically more important, and so they receive more attention to the damage caused by earthquakes. So how important is the value of objects in doing the plan for the mitigation of earthquake risks? Do you include it, or does museum include it when asking for this sort of assessment?
Thank you. And that idea of joining small masses together, that's exactly right. You're changing the aspect ratio to something that's more stable. So excellent idea, low cost, and obviously really effective. That's great. Congratulations. Boy, you know, the concept of judging the value of an object in order to decide which gets more resources in terms of protection. The metrics of that can and will change depending upon the museum, depending upon often the people giving advice and depending upon the person who makes the final decision. Sometimes it's based on the rarity of the object. Sometimes it's based on the fragility of the object. And sometimes it's based on religious reasons. It's whether you have 5 of those things of equal value, or whether you have only 1, and whether that 1 is the only one in the world. I mean, all of those things play into this idea of valuation. And I think the exercise that's the most effective is to go through all of those categories, to say, well, what's worth the most money if we lost it? What is irreplaceable because it's the only one? What do we have 5 of, or 10 of, or 1,000 of that it would be sad to lose it, but what is only a supportive example? What is of religious or cultural importance in our collection? What is the object or the group of objects, or the painting, or whatever, that represents the institution, right? You go through all of that, and then you bring it all together to try to find some sort of compromise. You cannot, in one go, protect everything, but you can give different levels of protection to everything, right? So I'm sorry, I don't have a specific answer for you, because I think that is very specific to the institution and to their collection and to how they approach preservation and stewardship and what they think is important. It is, however, I can say with some confidence, something that museums don't often do. They just don't. They, like a lot of conservators and a lot of preservationists, live in this kind of ideal world where we're going to save everything, right? And we are slowly coming to the realization that we can't save everything, that we have limited resources and we have limited time. And we have to put priorities on some things. So if you bring together a group of people and you ask the conservators, how do you want to prioritize? They will tell you by tradition that everything is of equal importance. You want to save everything, right? But they might be more inclined to make divisions based on what is the most fragile. What is, for example, if you had to evacuate a collection, what is the easiest to move, right? What can you get out faster? That might then put those objects on the top of the priority list for the conservator, but then the curator, the art historian, the director might come in and go, well, that's all fine, but what we really need to do is save this object, because this object is incredibly rare, it represents the institution, and then some compromise is struck. Or someone is in the position to make the final decision, right? But I don't, unless you have a suggestion, I don't think that there's a kind of standard rule for how priorities should be set. I think that in the end kind of boils down to the priorities of the institution and how they want to divide them. What's important is that they are looked at, is that this is addressed, because I don't think it's addressed in a lot of institutions.
Thank you.
Yeah,
thank you, Jerry. And that was exactly what I expected to hear. So
But is it what you believe?
No, yeah, I do believe.
Oh, okay, all right.
No, because for some people, all of this information that we received yesterday and today could be overwhelming when thinking of collections in general and in total. For some, it might sound like science fiction, you know. At least for the developing countries, at least from where I come from. But certainly the prioritization is a necessity in this area as well as in others in conservation. So thank you for your answer.
And I'm glad you said that, because it always worries me, you know, how information like this will be received. You know, because it's, as I said, conservators are used to the idea of dealing with lots of chemistry. We're not used to the idea of dealing with engineering principles or strength characteristics or physics. We're just not. It's not in our education. It should be, but it's not. And so all of these seem like overwhelming exotic aspects, but they are tools that, if you become generally familiar with them, you can tap into the expertise of other professions. And there are tools that you can use however you wish, however you want to apply them to whatever priority situation you have. One just has to have a kind of blind faith, I guess, that it will eventually make sense and it will be applicable.
Thank you, Veljko, for asking the question, and thank you, Jerry, for responding. We shall stick to the topic of storage rooms for a few more minutes. There's a question in the chat from Aida Grga. She thanks you, Jerry, for the interesting lecture. And the question is as follows. What would be the advice for fixing the shelves in the storage, to arrange the shelves in square shape or H shape to lower the shaking stress and damages?
Well, if the shelves are freestanding in the middle of the room, yes. I mean, anchoring them to the floor, or if you can't do that, arranging them into a more stable shape by bolting them together. If they're up against the wall, there are a myriad of ways in which you can anchor the shelves. The one thing you cannot do and should not do is go in with a piece of cheap wire and a couple of screws and say that's anchored. The anchors have to resist at least 3 times the weight of the total shelving, right? So you have to get a substantial anchor in there to make sure that they're solid. But the person actually answered their own question. You know, these are ways of doing it, and they should be done.
Excellent. Thank you. I would now like to ask if he is present with us, Vlatko Čakširan. He is the director of the Sisak Municipal Museum. And you saw one of the images that you included in your presentation was taken at his museum. So Vlatko, if you're here, I would actually like to ask you a little bit to tell us something about how you prepared the shelves or the shelving for the museum collections that were brought to your institution from Petrinja and that are temporarily stored at your museum. I know that the technicians of the Sisak Municipal Museum, they had to prepare everything for these objects that are temporarily homeless, so to speak. So Vlatko, if you are here, maybe you can join us and say,
yes.
Super.
Yes.
Over to you.
Thank you very much, Agita. Hello to everyone. So before the earthquake, I don't have any experience in the in some disasters like this. Last year I was 34 years and I look the earthquake only on the films or something like that. But what is the most important thing in Sisak, what is most dangerous thing are the floodings or the rivers. So we always think about water and damages and so on, but earthquake is always something what is behind, and it's something what happens in other parts of the world, like in America, Japan, or something like that. But after the earthquake, I have great informations from Ivo Valigia, from Jacqueline Balen, from the Archaeology Museum from Zagreb, from Sagita, and so on. They give me some very good informations that are helping me and my colleagues from the museum to evacuate the artifacts from our museum and to arrange our exhibition place for the storage. It's you know, when I was looking at your examples, it's I call it the earthquake logic. You know, after the earthquake, we anchored all our shelves and our showcases. We put permanent anchors made by the wood and something like that. We also put another things to fix the artifacts, the pictures from the Krsto Hegedeć gallery from Petrinja, the artifacts from our museum, and you know, after the earthquake, everything is different in our museum.
Thank you, Vlatko, for the comment. So yeah, Vlatko's museum, actually, it's not just one building. They are in charge even of an archaeological site. They have some historical objects. So there were a lot of duties on your hand. In addition to having to keep an eye on what's happening with your own collection, you also had to secure this temporary storage for the objects from another institution. And so maybe you mentioned, Vlatko, also that our own Dunja Vranešević and Iva Valigia, they were both involved in storing these objects that were moved to your building from another institution. Maybe we can have Dunja and Iva to say a few words about that, and then we can maybe discuss a little more this issue that you also brought up, Vlatko, of what is happening with the furniture, with the showcases and the pedestals within the exhibition area. So Iva or Dunja, do you want to maybe add something to what Vlatko has already said?
Before we comment on Petrinja, I would just like to say that I read in literature about making priority lists for evacuation. So which objects would you save in some kind of earthquake or hazard? It is said that we choose up to maximum 4% of museum collections of objects. Yeah, only 4%, because you can't save everything, of course, and you need to make a list that will be acceptable so you can save it on time. So I don't know if that is correct. Maybe it depends on collection, on size of the collection, of course, on time you have. But when you are planning ahead, you think of only 4 or 5% of the collection.
Could I just comment on that, because I dealt with the museum in St. Louis, Missouri, near the epicenter of the greatest earthquake in the United States, and they were talking about 6%, right? The problem started, the real discussion started in what represents 6%, right? So you can stabilize, let's say, one part of the storeroom by screwing down the shelves and putting some packing paper around it, and that's 6%, right? It's good to think about focusing on a small, narrow part of the collection. The real problem becomes, the discussion starts when what composes that 6%. Yeah.
Yes, I think everyone has that problem, of course. And I think a reorg method is really helpful here, because they have a rule that every object in the storage needs to be found in 3 minutes tops. So they arrange it so you can find it easily, and we try to use the same method or similar method to Petrinja, because we've relocated and tagged every object, every box, every shelf with some kind of similar but simple location codes, so we could find it in every every second in every time, and we did it in Excel sheets so we can have it on the go. And I think it was very useful. What do you think, Eva?
Well, the problem is, it was important to do the relocation of all the museum items from Petrinja to Vlatko's museum in Sisak, and to put it in a way so professional that they do not have at the moment when he gets employed in the gallery, that person can locate all the items and know that it's really there. It was a demanding task because the gallery or the storage was really damaged, and we weren't allowed to enter the building. So Croatian Rescue Services, they took through the roof window the smaller pieces, the bigger ones they were taking down the stairs, but we weren't allowed to go in. So that's another, you already mentioned when an earthquake strikes, you have to take in consideration the after damages. You have to take in consideration that all the people that are involved are within the safe area or within the safe bubble, let's say. So we tried to respect that as much as we could, and I think we did. And we also knew the procedure when we arrived to Sisak's Municipal Museum. Vlatko told us exactly which are the corridors where we can go, what will we do when the ground shakes again, because we had a constant shaking, and how to react, or what to do in certain kind of situations, which is I think very important. The relocation was done successfully. The future is what we wait for now. I mean, I don't know what will be the future, when the gallery will be rebuilt, when when his museum will be rebuilt in total, when everything will go back to normal. Maybe 5 years, 10 years, I don't know, long time, I'm sure, unfortunately.
Eva, so those objects from Petrinja Museum are now kept at Vlatko's museum. And can I just ask you, so we mentioned earlier that the shelves on which these objects are placed, that they are securely anchored, which Vlatko's team made sure of. But can I just ask you, once you place the objects on the shelves, were there any measures of precaution that you took not to have the objects turn over? Because as you said, the ground was constantly shaking, and I presume that these aftershocks, I mean, the people still feel them in the Sisak Petrinja area, unfortunately.
Yes, all the shelves were metal shelves, so we tried to arrange all the items, whether in the boxes and then on the shelves, or if they were the heavier, bigger ones, they went on the ground shelf. And as well, we took some we made some temporarily secure bands, like diagonal or how do you call this? Not vertical, but this way, and so they would be secured. I think Vlatko can confirm that everything is still in place.
Yeah, it's still in place and secured.
And
I just want to say, I just want to say that we have lots of help from Ministry of Culture of Republic of Croatia in case of packaging materials and boxes. So this is very important when we talk about the putting the artifacts on the safe places.
Preparing the material, wrapping material.
Yeah.
Excellent. Thank you, everyone, for your contribution to the discussion. Dunja, do you want to maybe we can now? I know that we had said that this would last 2.5 hours, but let's, if Jerry doesn't mind, let's take a few more minutes to discuss some extra issues. Maybe I would like to ask actually the colleague from the Museum of Arts and Crafts in Zagreb, Anna, if she would like to join in our live discussion discussion now. And maybe now we can talk a little bit about the exhibition area, so the permanent display. And Anna, if you can maybe tell us something about the behavior or the response of the exhibition furniture, so the showcases, maybe the pedestals within your museum, which is a big museum, and I know that each room has a different setting, but maybe some general observations that you could make. I mean, how this furniture withstood the earthquake in March last year.
Yes, hi everybody. I'm a conservatory restorer from the Museum of Arts and Crafts, as Sakida said. My name is Anna. And basically, before I tell you about the furniture and everything, maybe it's important to say that the Museum of Arts and Crafts, it's a giant building. There's 8,000 square meters of exhibition space. Parts of the building were built 140 years ago. Some were built 120 years ago, have been remodeled through time, and they have been affected by the earthquake in different ways. So not all parts of the building responded in the same way. Hence, not every part of our, let's say, collections was equally damaged. Obviously, the higher we went up, the damage was worse. The third floor, which housed some of the most sensitive collections in terms of ceramics, clocks, glass and such. We did have those hanging glass cases. Luckily, a good portion of the objects was kind of adhered down with museum wax and museum gel, but not all, obviously. So the objects that were damaged were the ones that were completely loose, that had a very high center of gravity, and were just literally just flat on the floor and moving around. Anything that was fixed to the wall withstood everything, including whether it was on a raised pedestal. Most of the pedestals in the museum are part of the architecture of the space itself, so very few are freestanding. The ones that are freestanding, luckily none of them turned over, probably because most of the objects on them were very heavy. So they, took a little bit more of the forces. One of the biggest row of damage that happened was actually on the cascades that were showcasing our clocks. Most of the clocks turned face forward because most of the mechanisms in clocks are very high up, taking the center of gravity high up. So we had a lot of damage there. Actually, one of the photos that Jerry showed was of one of the clocks, and on the side you can see the cascades and a clock leaning over or leaning back. So the cases that were built into the architecture were fine. However, just as Jerry showed, a lot of the objects fell on the side of the cases, and we had a lot of problems while opening the cases and taking them apart in order to save the objects. So literally we had a whole range of everything that Jerry has shown us, and we have definitely learned our lessons in terms of certain kinds of furniture that are not to be allowed. And I wanted to tie in onto the everyday vibrations. Our museum is next to one of the most frequented tram lines in Zagreb, and on an average there's a tram passing by in both directions every 30 seconds to a minute. Since the earthquake, you can definitely feel the building shaking a lot more. I think everybody, even the people from the MDC, from the Museum Documentation Center, have probably the same experience. And I have a furnace, a ceramic furnace that was restored in the early 90s. It's a friar. Many of you who have been to the museum know of a friar kneeling down and praying. Well, one of his hands has been restored. And as the trams pass by and as the vibrations accumulate over time, his hand kind of falls out. And then every few months I go in there and I put it back in. So yes, that happens, and it's something that you need to observe on a longer period of time and kind of live with the collections and the objects. And that's why I agree with Jerry that you need to have an individual approach to every museum and every collection.
Thank you very much, Anna. Dunja, over to you for the questions from chat.
Yes, we have one question from chat from Katerina. She says, "Thank you very much for all of the interesting information. My question is, Sculptures and shelves were talked about at large, but what about paintings? Are there any specific steps taken to ensure their safety in such situations, given they can fall off the wall and potentially be damaged in an earthquake? And what about storing them safely?
Thank you. I mentioned a little bit about paintings or anything that's hung on the wall. And the issue ranges from make sure that the hook or the connection to the wall is sufficient for the weight of the object. Make sure the wire, if you're using that, is sufficient and hasn't corroded or isn't of a gauge that's insufficient for the weight. We've found it very effective both on exhibition and in storage to anchor all four corners of the object to the wall so that the flat 2D object can't slide this way. And you know, the paintings aren't all going to do this. Some are going to do this and they're going to collide, right? So you want to stop them from swinging in plane, and you want to stop them from swinging forward and back, because when they do, they will hit the wall. There are myriad ways of doing that. You can hang it with two individual hooks. You can put hooks and restraints at the bottom. There are museums that create sort of frame structures that they connect to the painting frame, and those support frames attached to the wall. There's I think they're called, I can't remember what they're called, but they're sort of slots that slot into one another. So instead of hooks, you've got these planes that drop into one another. There's so many ways of doing that. The major point is you don't want to count on one point. You want to count on two, and you want to restrain the bottom from moving as well in storage and in the galleries.
Thank you so much, Jerry, for answering that question. I think that we don't have any new questions in the chat section. And so I think that we can finish it or sorry, Jerry, was there something that you wanted to ask?
I just want to make one final short comment. It occurs to me, listening to you and listening to other people, we're in a time period when there are so many things that we're looking back on and going, oh boy, boy, was that a disaster. Did we mess up, right? They range from social issues all the way to museums. And now we're left with a mess, right? We're left with a mess of the climate. We're left with a mess of museums that vibrate and are susceptible to damage. And we are of a time when we're looking back and trying to figure out how we can correct that mess. It requires some sacrifice, because we would rather, I'm sure, do lots of research in other areas. As I mentioned, conservation scientists would probably rather analyze Egyptian blue one more time, right? But we're duty bound as stewards of cultural heritage to look at the mess and address it. And there's plenty of opportunity for research and new frontiers in that area of contribution. Thanks. That was the comment.
Excellent. And I would also like to take the opportunity to say that it is so very and immensely important to also speak about this mess and to analyze the mistakes and to learn from them, not to hide them under the carpet and pretend that nothing happened. Today you were showing many photographs that were taken in the museums in Zagreb. And for us, it was an excellent thing that you included those examples in your presentation, because we can learn from those things and we want to learn from those things. And also this whole workshop, as I explained yesterday in the introductory talk, this whole, our collaboration on this topic, it started when the Museum of Arts and Crafts shared some images of the damages in their collection, which are reposted, and you saw it. So it just goes to show that we can only benefit from openly talking about some problematic issues, and so let's be honest, and also let's be open to the possibility of improving things. So and thank you again, Jerry, really for all the help that you have provided us for not just for this workshop, but I mentioned your wonderful contribution throughout last year and this whole year. So we are immensely grateful for that. And thank you for this another fantastic day of fantastic lectures. Thank you to everyone in the audience for sticking with us. And I know that tomorrow, when Mackenzie Lowry shares his practical tips, I think that all ears will be very sharp. Having said that, I will just turn it over to Dunja for some closing remarks, and then we will wrap it for today. Dunja.
I would just like to point out what Jerry said, that it also is shown in these pictures that were shared by museums, that museums must unite and work together and share their experience, because we only can come up with solutions together, not individually. Yes. And I would like to thank Jerry, because I think it was very interesting, and especially when you started with those videos from Kobe, Japan, from testing, and you can see that building that survived the earthquake, the testing, but inside everything was mess. So it really shows of importance of protecting the collections from the inside, not just the building itself. Yes. And I would just like to say to everyone else, thank you for joining us. Thank you for listening very closely. Thank you for your questions. And tomorrow we start at 3 p.m. Also, and we will hear Mackenzie also, and Jerry, of course. And you have the link in your emails for the third day. Yes.
Excellent. Bye-bye, everyone, and see you tomorrow.
Bye. Thank you.